Hello friends, I welcome you in lecture number 12 on partial ordering. In this lecture we are going to understand what is greatest and least element in a partially ordered set. So first we understand the definition and then we will take examples to understand this definition. So definition is, suppose we have some partially ordered set denoted by capital P, and this less than or equal to is the partial order relation on that set P. If there exists an element y in a partially ordered set P such that every element of that partial order set P is less than or equal to y, then y is called the greatest element in P relative to the partial order relation denoted by less than or equal to. If x is less than or equal to y for all x in a given set capital P, then this y is called the greatest element in a poset. Similarly, if there exists an element y belongs to P such that y is less than or equal to x for all x belongs to P, then y is called the least element in a poset P under the partial order relation less than or equal to. So definition is very easy. I repeat again, suppose I have some partially ordered set say P, and element y in this set P is called greatest element of this set if x is related to y for all x in a set P. If for every x in a given set P x is related to y, then y is called greatest element. And if y is related to x where x is any element of given set P, then in this case y is called least element of the given partially ordered set. Now it is not necessary that we always have greatest and least elements in a given set. So sometimes we will have greatest element in a given set and least element does not exist. Sometimes both do not exist. Sometimes both will exist. And greatest and least elements, if exist, are always unique. There is only one greatest element as well as there is only one least element in a given partially ordered set. And if I have totally ordered set or chain, the least and greatest elements always exist. In a totally ordered set, we know that if we take any two elements in a totally ordered set, then either x related to y or y related to x. So therefore, if I have totally ordered set or chain, then the least and the greatest elements always exist. Now I am taking this example. Suppose I have a set A having two elements and we are considering the partially ordered set which is power set of A with inclusion relation, and we have to determine the greatest and least elements in this partially ordered set. And here set A has two elements, therefore its power set has four elements. There are four subsets of this set A. So I have written these four subsets. Trivial subsets are empty set and set A itself, and other two subsets are set containing A and B. Now I have to decide whether greatest and least elements exist in this power set or not. So suppose I have greatest element in a given set. Here given set is power set of A. So suppose I consider that y is greatest element in the power set of A. Then by definition, if y is greatest element, then every element of given power set is related to y. Here relation is inclusion relation. That means y is greatest element of this power set of A if every element is related to y or every element of power set is a subset of Y. So we have to find out whether there exists any set or any element in a power set such that every other element is a subset of that set. So the obvious thing is that if we contain Y equal to set containing two elements AB, then all the sets in this power set are clearly subsets of this set AB, which is set A itself. Therefore, set A is the greatest element in this power set. I have written here that it is clear that phi is a subset of set having two elements AB. Similarly, singleton set A is a subset of AB, set containing B is a subset of AB, and this set itself is a subset of itself. Therefore, this set containing AB is greatest element in the partially ordered set power set of A with inclusion relation. Every element of this power set is related to set containing AB. Therefore, A equal to AB is the greatest element. Similarly, we have to decide least element. So for least element, I have to find out some element in a power set, say Y, such that Y is related to every other element in a power set. So that role is served by empty set. If we consider Y equal to empty set, then it is clear that empty set is subset of each of these sets. Therefore, empty set is going to be the least element. So here I have written empty set is a subset of itself, then empty set is a subset of set containing A. Similarly, empty set is subset of these two sets. Therefore, empty set is related to every subset of A. Therefore, empty set is the least element in the power set of A with inclusion relation. And we can use hash diagram also to decide greatest and least elements. So if we have only one element at the top of the hash diagram, then that is going to be greatest element, and if there is only one element at the bottom of the hash diagram, then that element is the least element of that partially ordered set. Now for hash diagram, we can see there are four elements here, and we know that phi is related to set containing A and B, and these two sets contain empty set phi. So I will join these two by line segments because phi is covered by these two sets. Similarly, set containing AB is a cover of these two sets. So we will have this type of hash diagram, and we can see at the bottom we have only one set, that is empty set, and it is the least element, and at the top of the hash diagram we also have only one element, that is going to be the greatest element of the given partially ordered set. So this is the hash diagram. Now this is not true for this set A containing two elements only, but in general we can say that suppose we have any finite set, suppose A is any finite set, and if we are considering power set of A with inclusion relation, then we know that this is always a partially ordered set, and we know that power set of A is the collection of all subsets of A. Therefore, we can say that if we take any subset T of A, then it is going to be subset of A. If we take any element in a power set of A, then power set of A contains all subsets of A. So any element in the power set of A is a subset of A. Therefore, set A is the greatest element. No matter which set we are considering, if we have finite number of elements in set A, then T is a subset of A for all T in a power set of A. Therefore, set A is the greatest element in the power set of A. And same thing for empty set. If we take empty set, then empty set is a subset of T for any t in the power set of A. So empty set is going to be the least element. So remember this general problem also. If we have capital A as a finite set and suppose we have partially ordered set which is power set of A with inclusion relation, then the greatest element of this partially ordered set is the set A and the least element is the empty set. We consider another example. Here I have taken divisibility relation on the set having these elements 2, 3, 6, 12, 24 and 36, and we have to decide the least and the greatest elements. So we can see greatest element, suppose I denote this set by P, then greatest element is the element Y in a given set P such that X is related to Y for every X in a given set P. Now here relation is divisibility relation, so we have to search for that Y such that X divides Y for every X in a given set P. So if there is some element Y in this set which is divisible by every other element of that set and with itself also, then that element is going to be the greatest element. So we can check for 36. We know that 2 divides 36, 3 divides 36, 6 divides 36, 12 also divides 36, but 24 cannot divide 36. So 36 will not be the greatest element. And if I take 24, then 24 is not divisible by 36. So I can say that there is no element Y in this set such that X divides Y for all X belongs to P. Therefore, this partially ordered set has no greatest element, or greatest element does not exist in this partially ordered set. Now what about least element? So least element is that element, suppose Y is the least element, then Y is related to X for every X in a given set P. Here our relation is divisibility relation, so we have to decide that element Y in a given set P such that Y divides X for every X in a given set P. So here if I consider, I check for 2, then I know that 2 cannot divide 3. So this condition is not satisfied for Y equal to 2. Similarly, if I take 3, then 3 cannot divide 2. So that is not possible for 3 also. If I take 6, then 6 cannot divide 2 and 6 cannot divide 3. So in this way you can verify that there is no Y in this set such that Y divides X for every X belongs to P. Therefore, this partially ordered set has no greatest as well as no least elements. And we can use hash diagram also. Suppose I am using hash diagram of this partially ordered set. Then this is the hash diagram. You can see at the bottom I have 2 elements, 2 and 3. And at the top also I have 2 elements. So this set has no greatest and no least element. We can write that the least and the greatest elements do not exist. Least and the greatest elements do not exist in a given partially ordered set. In a given partially ordered set. So in this way we are using the definition to decide whether greatest or least elements exist or not. Now I have taken another example also. Here I have taken this set of positive integers under divisibility relation. there are infinite number of elements in this Z plus, and I have to decide whether greatest and the least elements exist or not. First we talk about least element. Definition is that y belongs to Z plus is the least element if y is related to x for every x in a given set. Here given set is Z plus. Now our relation is divisibility relation, so y divides x. If y divides x for any x in the given set, then y will be the least element in this poset. And we can see if we take y equal to 1, then we know that 1 divides x for every x in Z plus, therefore 1 is the least element. So let me write for least element first, that it is clear that clearly 1 divides n. We use small n for positive integers for all n in the set of integers. Therefore this 1 is the least element in a given poset. Least element in this partially ordered set Z plus under divisibility relation. Now for greatest element, I have to think for that element y in Z plus such that x is related to y for all x in Z plus. I have to decide, or I have to check whether I can find out any positive integer such that x divides y for every x in Z plus. So it is obvious that this is not possible because there are infinite number of positive integers, so we cannot find out any y in Z plus such that this happens, because we have infinite number of elements in Z plus. So we cannot decide that what is our y, or there is no y in Z plus such that x divides y for every x belongs to Z plus. This means the greatest element does not exist. So that I have written here. Since there is no integer that is divisible by all positive integers, that means there is no y such that this happens, that x divides y for all x belongs to Z plus. There does not exist any x such that x divides y. This I can rewrite as there is no integer, that is there is no integer y that is divisible by all positive integers x. Therefore there is no greatest element in this partially ordered set with divisibility relation. And integer 1 is the least element because 1 divides n for all n in the set of positive integers. So in this way we can decide the greatest and the least elements in a given partially ordered set. We end this session by again revising these two definitions. Suppose I have a partially ordered set P, then an element y belongs to P is called greatest element of set P if x is related to y for every x in a set P, and y is called least element if y is related to x for every x belongs to P in a where P is a given partially ordered set. If we are talking about greatest element, y is greater than or equal to x, and if we are talking about least element, y is less than or equal to x, where x is any element of a given partially ordered set. So remember these two definitions, they are important, and they can ask you to locate greatest and least elements of a partially ordered set. And this is all about this session. I hope you like it. Thanks for watching.